We've now gotten a better look at what the derivative really is under the hood, the limit of ratios of changes as those changes shrink to zero. Now we'll see how limits involving infinity let us get a similar understanding of the integral. Here's a riddle for you. When can nothing become something? That's a question that's plagued mathematicians since ancient times. See, back in the 5th century BCE, great minds in ancient Greece were debating the true nature of the universe. One particular philosopher believed he had the answer. His name was Democritus, and he proposed that everything in the universe was composed of tiny indivisible pieces that he called atoms. These atoms were too small to be detected by the human eye, and there were infinitely many of them, coming in many different shapes and varieties. It was a radical theory. And by the way, when I say theory, I don't just mean a synonym for hypothesis, as in it was just a theory but we had no way of knowing whether it was true. Rather, I mean theory in the sense that scientists today actually use the word, a way of explaining why things work the way that they do. And according to Democritus and other atomists, these atoms could be used to explain everything in the universe. Unfortunately, there was no way of testing this theory, so it was forgotten for centuries. But as any student who's taken basic chemistry knows, atomic theory ended up being the basis of modern science. Democritus also applied his atomic theory to geometry. He successfully derived formulas for the volumes of cones and pyramids, showing that each was 1/3 the volume of a cylinder or prism with the same base and height. His key to doing this was to imagine them as being made up of tiny indivisible layers, circles for a cone or polygons for a pyramid, and then summing up all of the layers to get the volume of the whole shape. This kind of thinking led some people to believe that perhaps if matter could be broken into indivisible pieces, then so could space itself, and maybe even so could time. That idea didn't sit well with one particular philosopher of the time, Zeno of Elea. To drive his point home, Zeno came up with an interesting situation. Imagine you shoot an arrow. Now, freeze frame, and think of what happens to the arrow at just a single atomic point in time. In that single moment, Zeno says, the arrow clearly doesn't move. But time is made of many of these moments. And if the arrow doesn't move during any of those moments, then how does it move at all? This paradox, as well as others put forth by Zeno, baffled mathematicians for centuries to come, including Newton and Leibniz when they developed calculus to solve problems in physics, which of course involves describing motion. Nobody could deny that dividing space or time into infinitesimal chunks gave the right answers to a lot of hard problems. But at the same time, people just couldn't shake that nagging feeling that something didn't add up, literally. If you add up a whole bunch of nothings, even infinitely many nothings, how could you still get something? But that conundrum finally was met with a breakthrough with the advent of, you guessed it, limits. To make sense of integration, we need to talk about limits when the variable goes to infinity. Imagine we're looking at this function here, f of x equals 6x minus 1 over 3x plus 5. What happens to the value of f of x as x grows increasingly large, heading off toward infinity? We could always start to get an idea by looking at things numerically. Say we plug in x equals 10. Then if we work through it, we get 59 over 35, which comes out to about 1.6857. Okay, what if we let x equal 100? Now the numerator is 599, while the denominator is 305, and if we divide those, we get about 1.9639. If we keep going, letting x equal, say, 1,000, we get 5,999 divided by 3,005, which comes out to about 1.9963. By now you probably notice that these numbers seem to be getting closer and closer to 2. But how can we know for sure that that's the limit as x approaches infinity? Well, maybe we could try plugging in infinity into the top and bottom. Not a bad idea maybe, but this is one of those places where using infinity as a number can lead to some problems. When many people think of infinity, they think of it as a very loose, absorbing sort of number, at the end of the number line, whatever that means. For example, they'll say that infinity plus 1 is still just infinity, and so is infinity times 2. So, if we follow those rules and plug in infinity, we get infinity in the numerator, as well as the denominator. So we've actually got infinity over infinity. And you might be tempted to say that this is 1, because anything divided by itself is 1. But that doesn't make sense because our function was supposed to be approaching 2, not 1. Turns out infinity over infinity is another one of those indeterminate forms, just like 0 over 0. Depending on the situation, it can come out to anything, which means we need a little more finesse to deal with a situation like this. Let's do a bit of algebraic massage and multiply both the numerator and denominator by 1 over x, distributing it through. We can safely do this because if x is approaching infinity, we certainly don't have to worry about it being anywhere close to 0. So if we distribute those 1 over x's and clean things up a bit, we get 6 minus 1 over x over 3 plus 5 over x. How does that help us? Well, now as x gets really large, 1 over x gets really small, and so does 5 over x for that matter. So as x approaches infinity, the two fractions here approach 0. So in the limit, they'd be 0. That leaves us with 6 over 3, which does in fact equal 2 as expected. So the limit of f of x as x approaches infinity is 2. And if we'd approached negative infinity, we would have gotten the exact same thing. Think for a bit on your own about why that happens. So essentially, since the numerator and denominator were growing at comparable rates, both being linear functions, their ratio ended up approaching a limit of 2. But what if the numerator and denominator grow at drastically different rates? What if we change the denominator to, say, 3x squared plus 5? Now, the denominator grows much faster than the numerator, and the overall fraction shrinks down closer and closer to 0. We can show this by multiplying the numerator and denominator by 1 over x squared, since x squared is the highest power of x, appearing in either part of the fraction. And then the numerator becomes 6 over x minus 1 over x squared, while the denominator becomes 3 plus 5 over x squared. So as x approaches infinity, that whole numerator shrinks down to 0, while the denominator approaches 3, which means the whole fraction approaches a limit of 0. On the other hand, suppose we'd instead made the numerator have the larger power of x, say 6x cubed minus 1. Now the numerator is the one growing faster than the denominator can catch up, and as a result, the value of the fraction just keeps getting bigger and bigger. If we multiply the numerator and denominator by 1 over x cubed, the numerator comes out to 6 minus 1 over x cubed, while the denominator is 3 over x squared plus 5 over x cubed. As x gets huge, the numerator will always be close to 6, but the denominator will approach 0. That's taking on the form of a non-zero number divided by 0, so we should be expecting an infinite answer. And since the denominator is approaching from the positive side, which you can check, we conclude that the function is indeed approaching positive infinity. By the way, you can also show that as x approaches negative infinity, the fraction as a whole still approaches positive infinity. Try seeing what happens when you plug in large negative values into this modified fraction to see why that's the case. So all in all, depending on the rates at which the top and bottom of the fraction grow, a limit of the form infinity over infinity could approach basically any number, including infinity. But you might have noticed that the only thing that really matters here is the leading term in the numerator and the denominator. As x grows larger and larger, the fastest growing term dominates the behavior of the function. So in practice, we can sometimes take a bit of a shortcut and ignore any terms of the numerator and denominator other than the leading term of each. In the long run, that's the only term that'll matter, so it'll control the end behavior of either function. Then we can just look at the ratio between those leading terms as x grows larger, and that makes finding our limit much easier. Now, one last note about indeterminate forms. We've seen two of them so far, 0 divided by 0 and infinity divided by infinity. There's another form that's closely related to both of these, 0 times infinity. And if you think about it, that's the form that's suggested when we take a shape and break it down into an infinite number of infinitely thin pieces. So it should be no surprise that a limit of the form 0 times infinity can once again come out to just about anything, since those shapes could come in all sorts of different sizes. So if we can figure out how to deal with that, then we'll have a good idea of how to make integration actually work. We're almost there, but first we need to take a quick detour. Since integration is really all about summing things together, I want to tell you a well-known story about summations. The story of Carl Friedrich Gauss, one of the most influential mathematicians to ever live. Sometimes he's even called the Prince of Mathematics. But this story takes place when Gauss was just a little boy. As the story goes, in school one day, Gauss's teacher wanted to give his class some busy work. So he asked his students to add up all the numbers from 1 to 100. Most students started with 1 plus 2, then added 3, and then 4, and so on. But Gauss took a different approach. He noticed that if you add 1 plus 100, you get 101. And if you add 2 plus 99, you also get 101. If you add 3 plus 98, you get, wait for it, 101. That pattern keeps on going all the way until you get to 50 plus 51 equals 101. Since there are 50 such pairs, if we add everything up, we get 101 times 50, which is 5050. Back to the story, it said that Gauss wrote the answer down on his slate after only a few minutes, stood up, put it on his teacher's desk, saying, "Here it lies," and sat back down in his chair looking smug for the rest of class. Now, if you ask me, this story is about as believable as those stories you see posted all over social media, where everybody claps at the end, and the kid's name was Albert Einstein. But the cool thing about this story is that it has a mathematical result embedded in it. If you're adding up the integers from 1 through n, the result is n plus 1 times n over 2. The last number plus the first number times the number of pairs. And yes, this even works if n is odd, and I invite you to figure out why. So for example, if you added up all the numbers from 1 to 1,000, the result would be 1,000 plus 1 times 1,000 divided by 2, which would give you 500,500. Pretty neat. It just so happens that there are other formulas for how to add up sums of squares and sums of cubes. It's a little harder to give quick, beautiful, elegant explanations for these, though it is possible to find them if you look them up. For now, you could just take them for granted. And notice that in particular, each one gives you a polynomial that's 1 degree higher than the powers you're adding. The sum of squares is a cubic polynomial, and the sum of cubes is a quartic polynomial. And look at those coefficients, 1/3 n to the third, 1/4 n to the fourth. This is hinting at a deep connection between summations and integration that we do not have time to get into in this series. But that's what'll help us out when we finally do integration. Now that we've talked about limits at infinity as well as summations, we can finally look at how to define integration using limits. Let's look at a simple integral, the integral from 0 to 1 of x dx. Now, before you ask, yes, this is one we could just use simple geometry for. It's just a triangle with a base of 1 and a height of 1, so we should get an answer of 1/2. So why bother doing it this really long way? Well, the way we do this problem generalizes really nicely to other powers of x. So if this gives us the answer we're looking for, it suggests we're doing something right. So let's imagine we subdivide our interval from 0 to 1 into a total of n pieces of equal size. Then each interval will have a length of 1 over n, and that'll be the base of each rectangle we build on top of it. The first interval goes from 0 to 1 over n, the next goes from 1 over n to 2 over n, and so on, until the nth interval goes from n minus 1 over n to n over n, which is 1, our rightmost endpoint, just as expected. That takes care of the base of each rectangle, so what about the height? Well, that depends on what kind of sum we choose, but the simplest thing in this case is to always use the right endpoint to define each height. That way, since the function we're integrating is f of x equals x, the height of the first rectangle is 1 over n, the height of the second rectangle is 2 over n, and so on until the height of the nth rectangle is n over n. If we multiply base times height for each rectangle and add them up, we find that the total area of all the rectangles is 1 plus 2 plus 3 plus all the way to n divided by n squared. Now this works for the area of a finite number of rectangles, but this is still just an approximation of the true area we're looking for. So what we want to do is find the limit as the number of rectangles goes to infinity, which means that the rectangles are getting thinner and thinner. So what happens as n goes to infinity in this expression? Look closely at the numerator. That's just the sum of all the integers from 1 to n. We just saw how to do that. That's just n plus 1 times n over 2. So if we clean things up a bit algebraically, we're taking the limit as n approaches infinity of n squared plus n over 2n squared. And we also know how to compute that limit. Either multiply the numerator and denominator by 1 over n squared, or just drop everything but the leading terms, but either way, you should find that the limit is indeed 1/2, which is exactly what we expected for the integral from 0 to 1 of x dx. It checks out. We did it. This technique we used here is what Bernard Riemann, one of the people who cleaned up those infinitesimal-based definitions in calculus, used to define the integral in general. First, we add up all the areas of the rectangles, height times base, which we usually call a Riemann sum. Then, we take a limit as the number of rectangles goes to infinity, making sure that the size of the largest interval always shrinks down to 0. As long as that limit exists, no matter how we make those subintervals, it always gives the value of the integral that we're looking for. Wait a minute, there's that phrase again, as long as that limit exists. Are there certain functions for which the integral isn't defined, where this limit breaks down just like derivatives did when functions weren't differentiable? Turns out the answer is yes. But I won't go into too much detail because those functions are a lot harder to draw and you're unlikely to come across them in practice. But there is one particularly infamous example, the so-called Dirichlet function. Imagine a function that if you plug in a rational number, you get 1. But if you plug in an irrational number, you get 0. That would be a pretty weird looking function, since it would be constantly jumping back and forth between 0 and 1. And that means that by choosing just the right places to draw your rectangles, you could get just about any area you want. So yeah, there are some pretty weird edge cases. But just about any function you'll actually encounter in real-world situations is likely to be integrable. And that means our definition works no matter what kind of Riemann sum we choose. This limit definition of integration is what lets us finally resolve those paradoxical notions brought up by Zeno's arrow. We no longer have to wrestle with what happens to the arrow in a single infinitesimal instant. All we need to do is consider its motion on small but definite intervals of time, and then look at what happens to the sum of those motions as we take a limit, letting the number of subintervals approach infinity. At no point are we adding up a bunch of nothings and expecting to get something. Zeno's arrow, no longer frozen in time, is finally free to fly.